Hello friends, today we'll be going to start with step refinement process. As whenever we are designing the algorithm, we have to do the rectification or you can say refinement in each step. We can do that one to enhance the time complexity or you can say space complexity. So today we'll take an example, that is a number is prime or not. So what we'll do today, we'll take the example a number is prime or not, and we'll use or we'll find the algorithm by taking the help of step refinement process. In each step we'll do some rectification or refinement, and at the end we'll get the time complexity of that algorithm. So whenever suppose you are taking like this, P of n is either you can get it true or false, means a number maybe it is a prime or not. Here n is the input and p is the function. Here n is the input and p is the function, means you are applying the p function to the n input and you are finding out that it is true or false. Let's start. So whenever we are saying a number is prime or not, first of all we can think about the number like 1, 2, 3, 4, 5, 6 like this. Prime means the number which is divisible by 1 and itself. So whenever we are taking care of this number from the first statement, that is it is divisible by itself or you can say by the 1. So we can find it out that the number should be odd. If that is a number odd, if the number is odd, then only that number can be coming under the prime number, otherwise not. So we can take a number is prime if that number is odd. Now consider the second step. 2 is the number which is an even number but it is a prime number. So here another refinement we are doing now. If number is 2 is equal to 2, then also it is coming under as a prime number. So now we can combine these two strategy, that if you are saying a number is prime or not, the first step is that it should be a odd number, and second thing is that if this is 2, then also it will be a prime number. So now we have to check the number is prime or not for the number which are odd. Then we can check that if it is 2, it is a prime number, because already you know this. So next step we can do the next refinement. Okay, suppose the number n is given to you. You have to find out the divisors. Divisors means which number can divide this n. So you can start from 2 to n. And if you are considering 2 to n, the time complexity will be n. Somehow you can say the time complexity of this one will be n, because you have to start from 2, 3, 4, 5, 6, all the numbers n. But as you know that n is a odd number, can even the odd number will be divisible by 4, can be divisible by 6, can be divisible by 8? No, it won't be possible. So what we can do, now we can get the next refinement, that the n can be only divided by the numbers which will be odd. So you can say 3, 5, 7, this number you can find it out. And whenever you are doing this one, the time complexity will be n by 2. So you have done some refinement, that from time complexity n we are coming to n by 2. Next again we have to do some refinement. So the first step what we did, we have taken the number is a prime or not. Then what we did, we have taken the number that will be odd. The first step we have did, that is a odd number, or you can say it will be number 2. Then second step what we did some refinement, that we have checked all the n number of elements, that is order of n time complexity. Then we have checked it only with the odd number, that is the complexity will be n by 2. Now you can say some refinement we have did over here. Next step what we have to do next, if you are taking 3, 5, 7 as the divisors, 3, 5, 7, 9. Suppose the number is, you can say 97, n equal to 97. So is it possible 97 will be divisible by 95? I don't think it will be possible. Next 93. Next you can find it out 91. So where it is possible that 97 can be divisible? It will be divided by 2. 97 is divisible by what particular number we have to check? 97 divided by 2. So whatever we are getting, that upper bound we can take it 48. So now we don't have to check the particular 97 with the all numbers 3, 5, 7, 9, 91, 93, 95. No. What we can do? We can make it 48. We can make it maximum 48, or 48 you can say that it will be 47. Now again, if you are checking this condition, again the time complexity will be n by 4, because again you are going for n by 2, order of n by 4. So this is the refinement we have did. Next step, whenever we are saying 47, just think about that root over of 97. Root over of 97. That whatever you are getting, that will be the maximum, you can say, divisible number. It will be possible for 97. So if you are taking the 97, you can say root over, you can take it, and whatever the number you are getting, suppose you are getting, what is the number you are getting? Suppose 9 point something you are getting. So if you are taking the lower bound, maximum 9. So you can consider only n, that is you can say root over of 97, that is 9. This number you can consider and you can check it out that 97 is prime or not. So again you can say the time complexity will be reduced, and the time complexity we can write down like this, root over of n divided by 4. So now you can check the thing that we are checking the number is prime or not. First of all, we are getting order of n, the time complexity, then order of n by 2, then order of n by 4, then you can say order of root over of n divided by 4. So like this, the time complexity reduces whenever you are doing the refinement process in a particular algorithm. So like this refinement process can be used in any pseudocode and algorithm to get the proper implementation. Next step is that how to prove the correctness of this one. How to prove the correctness of this particular algorithm. So for the correctness we have to use the Fermat's little theorem. Fermat's little theorem. What the theorem says? Fermat's little theorem. What this theorem says? This theorem says that P of n mod n is equal to p, where n you can say check n is a prime number or not, that input you can check prime number, that input, and p is any number you check which is less than n. Again I am repeating, we have to use the Fermat's theorem, Fermat's little theorem to verify the algorithm correctness. So what is that? P of n mod n is equal to p. What is this n? This is the prime number, that is the input, and what is this p? Any number you can select that will be less than n. So we'll go for an example and we'll prove it, is it correct or not. So you can take it 2 to the power 7 mod 7 is equal to 2 or not, that we have to prove it. Okay, so n is here 7 and we have taken the p value, that is 2, which is less than, you can say, your n. Okay, so you can say 2 to the power 7, that is 128. You can divide it by 7 and you are getting something 18, and you are getting some, you can say, your remainder as 2. This is the information we are going to get it, and once you are getting, you know that it is not divisible. Is 7 is, we are not getting that, you can say remainder you are getting 2. If, and this 7 is not divisible by 2, you know that one, but at the end we are getting the remainder as 2. So remainder is 2. So if this condition satisfy, the number is a prime number, means 7 is a prime number. Again I am repeating, this is a Fermat's little theorem. P of n mod n is equal to p, n equal to any prime number, p value should be less than n, you can take it. Here I had taken an example. 2 is the, you can say 7 is the prime number and 2 is the value of this p. 2 to the power 7 mod 7 is equal to 2. If it will be satisfied, it will be a prime number, otherwise not. So you are just doing all the calculation and you are getting that, you are getting the 2 over here. So it's a prime number. Next. So it has been proved for lakhs of numbers. From in between that some 16 numbers we are not getting that it is satisfying. So almost all the numbers which will be satisfy this Fermat's theorem, we can say that it is a prime number, or mathematically proven, you can say that one. So Fermat's theorem, it will be, if you can prove the Fermat theorem, then definitely we can say that the number is a prime number. Okay, thank you.